Algebraic Structures, Lecture 22, Solvability by Radicals. In this lecture, we will discuss solvability of polynomial equations by radicals. We start with the notion of a radical extension. So we actually start with the notion of a simple radical extension. Today, for simplicity, we will work in characteristic 0. So we always assume that all fields are of characteristic 0. So let K inside F be a field extension. Definition: this extension is called a simple radical extension, provided that there exist elements B in K and A in F, such that F is obtained from K by adjoining the element A, and A to the power K is equal to B for some positive integer K. For example, any field is a simple radical extension of itself. We can take B is equal to A, any non-zero element, and K being equal to 1. Second example, the extension of real numbers inside complex numbers is a simple radical extension because the complex numbers are obtained from the real numbers by adjoining the imaginary unit I, and that unit I squared is equal to -1, and -1 is a real number. Let us note that any simple radical extension is finite and algebraic. Now we can define the notion of a radical extension. Let K inside F be a field extension. Definition: this extension is called a radical extension, provided that there exists a chain of field extensions. K is equal to F0, F0 is a subset of F1, F1 is a subset of F2, and so on, all the way up to Fm, which is equal to F, where each step Fi inside Fi plus 1 is a simple radical extension. For example, any simple radical extension is of course a radical extension. And also it is easy to see that any radical extension is finite and algebraic. Note the transitivity that if K inside F and F inside capital K are radical extensions, then little k inside capital K is a radical extension as well. Here's another property. Let K inside F be a radical extension, and let capital K be an intermediate subfield. Then the extension of the capital K inside F is also a radical extension. Proof. Let us take a chain of simple radical extensions which start from a little k and end in the capital F, and we have m steps. Assume that at step I, the field Fi plus 1 is obtained from Fi by adjoining the element Ai, and that Ai to the power Ki is equal to Bi for some Bi in Fi and some positive integer Ki. Then, the following chain is a chain of simple radical extensions by definition. So we start from capital K, we adjoin to capital K the element A0, then we adjoin to capital K the elements A0 and A1, and so on, all the way up to the field where we adjoin to the capital K the elements A0, A1, and so on, Am-2, and then we go to F. So this is a chain of simple radical extensions. Note that some of the steps here might be identities, so equalities. And this proves our property. Here's another property. Let K inside F be a field extension, and let capital K and capital L be two intermediate fields. Let T be the minimum subfield of F, which contains both capital K and capital L. If both little k inside capital K and little k inside L are radical extensions, then little k inside T is a radical extension as well. Proof. Consider a chain of simple radical extensions which start from little k and go to capital K. Assume that at step I of this chain the field capital Ki plus 1 is obtained from capital Ki by adjoining the element ai, such that ai to the power ri is equal to bi, where bi is some element in capital Ki and ri is some positive integer. Similarly, consider a chain of simple radical extensions which start from little k and go to capital L. So the intermediate subfields are Li's. And assume that Li plus 1 is obtained from Li by adjoining some Ci, which, when raised to the power Si, gives us Di, where Di is an element of Li. And then we can consider the following chain of subfields, which start from little k and go to capital T. We start by adjoining to little k the element a0, then we adjoin a1 and so on all the way up to am-1. Then we adjoin c1, then c2, and then all the way up to all c's, and then we obtain the field C. This is a chain of simple radical extensions, and therefore the extension from little k to capital T is a radical extension. Now we can define the notion of solvability of equations by radicals. So let k be a field and g of x a polynomial with coefficients in k. Let f be the splitting field of g of x over k. Definition: we say that the equation g of x is equal to 0 is solvable by radicals, provided that our splitting field f is an intermediate subfield of some radical extension of our starting field little k inside some ending field capital K. Remark: note that solvability by radicals just means that each root of g of x can be expressed as some algebraic expression which involves all arithmetic operations together with the operations of taking nth roots, where n can be arbitrary and vary. And there is no claim that there is some kind of uniform expression or algorithm that solves all equations of a certain degree at the same time. So that's a property defined for one particular polynomial. Next, we discuss an important statement which is called Lagrange theorem. Let K inside F be a Galois field extension with the following properties. The Galois group of this extension is a cyclic group of order n. The field little k contains a primitive nth root of unity which we denote by zeta. Then the extension of k inside F is a simple radical extension. Proof: let sigma be a generator of our Galois group. Due to the linear independence of homomorphism theorems, which we proved earlier, there is an element A in F such that the element zeta defined in the following way. We start with A, and then we add zeta times sigma of A, and then we add zeta squared times sigma square of A, and so on, all the way up to zeta to the power n-1, sigma to the power n-1 of A is not 0. So we are using that the identity sigma, sigma squared, and so on, the element sigma to the power n-1, are different automorphisms of F, and so they must be linearly independent. So if I prescribe these scalars 1, zeta, zeta squared, and so on, this linear combination is non-zero, which means that there is an element A such that applying this linear combination to A, we get a non-zero element. That is our zeta. Then, from the definition of zeta, we have that sigma applied to zeta is equal to zeta inverse applied to zeta. Indeed, if we apply sigma, we get sigma of A plus zeta sigma squared of A plus and so on. And if we multiply this with zeta, we get theta back. And here we use that sigma to the power n is equal to the identity. Sigma is a generator of a cyclic group of order n. From this, we derive that sigma to the power I of zeta is equal to zeta to the power minus I of zeta, and this is of course not equal to zeta because zeta is a primitive nth root of unity. And this is true for any I between 0 and n, excluding 0 and n. So in other words, the identity element of G is the only element of G that fixes zeta. And from our Galois correspondence, it follows that theta cannot belong to any proper intermediate subfield of our extension. In other words, f is obtained from K by adjoining theta. At the same time, if we apply sigma to theta to the power n, this is equal to sigma of theta to the power n. This is equal to zeta to the power minus 1 theta to the power n. This is equal to zeta to the power minus n times theta to the power n. And since zeta is a primitive nth root of unity, zeta to the power minus n is the identity, so we get theta to the power n. And this means that theta to the power n belongs to K, because it is fixed by all elements of G. And this means exactly that our extension is a simple radical extension. Lagrange's theorem has the following very important corollary. Let K inside F be a Galois field extension such that K contains a primitive nth root of unity zeta, where n is the degree of this extension. Then K inside F is a radical extension if and only if the Galois group of this extension is solvable. Proof. If G is solvable, it has a subnormal series with abelian and hence also with cyclic subquotients. So we have G, it has a normal subgroup Gm-1, and then normal subgroup Gm-2, and then we can go all the way down to the identity. By the Galois correspondence, this gives us a chain of field extensions which start from K, which is a set of fixed points for the whole group G. We embed this into the set of the fixed points for G sub m-1, all the way up to the set of fixed points for G0, which is the identity, so this is F. And here, the Galois group of each step from the set of fixed points for Gi to the set of fixed points for Gi-1 is cyclic, because the subquotients here are cyclic. And from Lagrange's theorem, each of these steps is a simple radical extension. Hence, the extension from K to F is a radical extension. And the converse implication is similar. Next, let us discuss the solvability of the equation x to the power n minus 1 by radicals. So let us start with the observation that the equation x to the power n minus 1 is equal to 0 is always solvable by radicals. In fact, the splitting field of the polynomial x to the power n minus 1 over k is a simple radical extension of the original field. Indeed, it is obtained by adjoining to the original field some primitive nth root of unity, and then of course the nth power of this primitive nth root of unity is an element of k, because it's 1. So this is always a simple radical extension. Moreover, it is a Galois extension because F is a splitting field, and so this is a normal extension, and everything in characteristic 0 is separable, so that condition is automatic. So we always have a simple radical Galois extension when we extend k by some primitive nth root of unity. Each element of the Galois group is uniquely determined by its value at this primitive nth root of unity, and this value must be a power of this primitive nth root of unity. Let's say power m. So let's say that the exponent of the power is m. Now, mapping the element sigma to m is an injective homomorphism from our Galois group to the group of invertible elements of the ring Zn. This means that our Galois group is abelian because it embeds into an abelian group, and its order divides the cardinality of the group of invertible elements in Zn, and that group has cardinality phi of n, where phi is Euler's function. So this is our discussion of solvability of x to the power n minus 1 by radicals. Now we can formulate the main result for today, which is called Galois criterion. So let k be a field and g of x a polynomial with coefficients in k. then the equation g of x is equal to 0 is solvable by radicals if and only if its Galois group is solvable. Proof. Let f be the splitting field of g of x over k, and let g be the Galois group of f over k. Assume first that g is solvable, and let n be the cardinality of g. Let capital K be the field obtained from little k by adjoining the primitive nth root of unity. Then, of course, k is a radical extension of little k. Moreover, we may assume that capital K belongs to some finite extension P of our field F. That's because of the extension of homomorphism theorem. Let F prime be the minimal subfield of P which contains both capital F and capital K. Then it is easy to show that F prime is a Galois extension of capital K, and the Galois group of this extension is the subgroup of G which fixes the intersection of F and capital K. So this subgroup is a subgroup of a solvable group G, and hence it is solvable. And by the previous corollary, we can embed F prime, and hence also F, into some radical extension of K. So we can apply our previous corollary because now our field capital K contains a primitive nth root of unity. So this means exactly that our equation g of x is equal to 0 is solvable by radicals. So now let's prove the converse inclusion. So assume that our equation is solvable by radicals. Then the splitting field f is contained in some radical extension capital L of our field little k. Consider the corresponding chain of simple radical extensions which start from little k and go all the way up to capital L. And let n be the degree of this extension. Assume first that little k contains a primitive nth root of unity, which we denote by zeta. Then little k contains a primitive nth root of unity, where ni is the degree of any intermediate step in this chain of simple radical extensions. Now we can proceed by induction on the number of steps. If we have only one step, then the Galois group of L over K is abelian and hence solvable. So why is it abelian? It's abelian because of the following argument. So if L is obtained from K by adjoining an element A, such that A to the power R belongs to K, then any sigma in the Galois group is uniquely determined by the exponent m, such that sigma applied to the element A is equal to zeta to the power m, and then the element A. So this is because sigma to the power n is equal to the identity, so our Galois group has n elements. And from this it follows easily that any two elements of our Galois group commute. So here the rth root of b is A. To prove the induction step, let L1 prime be the minimal subfield of L, which contains both L1 and F. Then this field is a Galois extension of L1, whose Galois group is a subgroup of G consisting of all elements which fix L1 intersection with F. So we denote this subgroup by H. At the same time, similarly to the argument above, L1 is a Galois extension of K with an abelian Galois group. Therefore, L1 intersection with F is a Galois extension of K with an abelian Galois group, and we call it F. And from the Galois correspondence, we have that H is a normal subgroup of G, and the quotient of G modulo H is isomorphic to F. So we know that H is solvable by the inductive assumption, and since the quotient by H is abelian, it is also solvable, and so G is solvable. So here we use the transitivity of solvable groups. It remains to consider the case of an arbitrary field K. So we extend the field K to K prime by adjoining to our field K a primitive nth root of unity, and then we extend F to F prime by adjoining to F the same primitive nth root of unity. Then F prime is a Galois extension of K prime, whose Galois group is the subgroup of G consisting of all elements that fix K' intersection with F. And also K' is a Galois extension of K with an abelian Galois group. So this means that H is normal in G and G modulo H is abelian, and it remains to prove that H is solvable. But now H is a Galois group of F' over K', and K' has a primitive nth root of unity, so this reduces to the claim which we proved on the previous slide. And this completes our proof. So now we have proved our main theorem. Let us now discuss the so-called general polynomial equation. Let K be a field. Consider the field capital K, which is defined as the field of rational functions over the field little k in m variables t1, t2, and so on tm. Let f of x be the polynomial over capital K defined as follows: x to the power m plus t1 x to the power m minus 1 plus t2 x to the power m minus 2 plus and so on plus tm minus 1x plus tm. So that's a polynomial with coefficients in capital K. This should be m minus 2. Let f be the splitting field of this polynomial f of x. Claim: capital K inside capital F is the Galois extension whose Galois group is the symmetric group Sm. Proof: let xi1 and so on xim be the roots of our polynomial f of x in our splitting field capital F. Then, by Vieta's formulas, we can write each tr, each coefficient here, as minus 1 to the power r times the sum over all I1 and so on IR, where I1 is greater than or equal to 1, I2 is greater than I1 and so on, IR is greater than IR minus 1, and IR is less than or equal to m. And then we take the product xi I1, xi I2, and so on xi IR. Any algebraic dependence between these roots, of course, implies an algebraic dependence of T1 and so on Tm due to these formulas. But then this is not possible because T1 and so on Tm are variables of the field of rational functions, so they are algebraically independent. And this means that our xi1 and so on xim are also algebraically independent, which implies that f is the field of rational functions over k in these variables. But then, of course, any permutation of these variables defines an automorphism of the field, and this means that our symmetric group Sm is exactly the group of all automorphisms of this field, because any automorphism is also uniquely defined by its value on all variables. So this means that the Galois group of capital F over capital K is the symmetric group Sm. This has the following consequence, which is known as Abel-Ruffini's theorem. The general polynomial equation is solvable by radicals if and only if m is less than or equal to 4. So which means that the general polynomial equation of degree 5 and more is not solvable by radicals. Proof: we just checked that the Galois group of this general polynomial equation is the symmetric group Sm, and this group is solvable if and only if m is at most 4. And so our claim follows from the Galois criterion. One can even push this argument further and discuss non-solvability of equations over rational numbers. So proposition: for each m greater than or equal to 0, there is fm of x, a polynomial with rational coefficients, whose Galois group is isomorphic to Sm. So in particular, for m greater than or equal to 5, this polynomial fm of x is not solvable by radicals. So here is an idea of the proof. From the theory of finite fields, we know that for any prime p and for any positive integer degree, there exists an irreducible polynomial over Zp of that particular degree. Using this, one can construct polynomials a of x, b of x, and c of x with integer coefficients of degree m, and with leading term 1 such that modulo 2, so when prime is 2 and we reduce a of x modulo 2, then we get an irreducible polynomial. Modulo 3, the polynomial b of x has an irreducible factor of degree n minus 1, and modulo 5, the polynomial c of x has an irreducible factor of degree 2 and an irreducible factor of degree n minus 2 if n is odd, or of degree n minus 3 if n is even. When we construct these polynomials, we set f of x to be equal to 15a of x plus 10b of x plus 6c of x. And then one can show, using all our assumptions, that the Galois group of this equation, when described by its action on the roots of our polynomial f of x, contains a cycle of lengths n. This comes from the properties of a of x. A cycle of lengths n minus 1. This comes from the properties of b of x. And the transposition, which comes from the properties of c of x. And this implies that the Galois group is isomorphic to Sn. Some additional problems and questions at the end. Problem question 1. Prove with all details the transitivity of radical extensions. Problem question 2. Prove with all details that the Galois group of a Galois radical extension is solvable. Problem question 3. Prove with all details that mapping sigma to M is an injective homomorphism from the Galois group of f over k to z sub n star. So we had this in one of our proofs. Problem question 4. Prove with all details that f prime is a Galois extension of k with a Galois group. We take the Galois group of f over k, and then we take the intersection of f with k. So we also had this in one of our proofs. And problem question 5. Provide all details for the last part of the proof of Galois criterion. Thank you very much, and see you next time.